How many g-forces should a cell phone be able to withstand? That's the question I'm going to answer here today. Now, we've all dropped our cell phone before, and usually you drop it from about waist height, putting it in and out of your pocket. In fact, the military standards for handheld devices specify that it should be able to survive a 4-foot fall onto concrete with a sheet of plywood on top. So, that's the situation I'm going to try to consider for this cell phone drop. How many g-forces should a cell phone dropped from 4 feet or 1.2 meters be able to withstand? Since g-forces are really just a measure of acceleration, you might think that this is just a simple kinematics problem. We have the height, we have how far the object falls, and we can just plug it into the kinematic equations and then go from there. However, we'll run into some trouble. We'll easily be able to determine the velocity of the falling phone, but taking this velocity and translating it to an impact force and then an acceleration that the phone would feel will prove to be a bit difficult. The reason it proves to be difficult is because real-world collisions are inelastic, which means they don't conserve energy, or energy is lost during the collision. This lost energy has to go into the phone and the collision surface, and calculating this is a bit tricky. There's a few methods we can use. The knee-jerk reaction for impact force is to go right to Newton's second law. We can recast F equals ma in terms of momentum and write it as F equals the change in momentum over the change in time. Since momentum is related to velocity, we'll be able to plug in our impact velocity that we calculated earlier, and all we'll have to do is figure out the collision time, or the time it takes the collision to occur. Now this is easier said than done. Estimating these collision times is very hard for us to do just using the human eye. So we could, for example, take a huge range of possible collision times, plug them in, and see what the forces would look like. We see that the shorter the time, the higher the force, but frankly, this is a huge span over which the force could potentially be. And another point to make about this is that this is only the average force. Even if we did get a high-speed camera and precisely timed the time that the phone spent in contact with the ground, we'd only have the average force experienced, and we wouldn't be able to speak to whether at some point the force the phone experienced was higher than this average. So, we'll have to try to consider a better way of going about solving the problem. Another way to do this would be to use the work-energy principle, using the fact that the net work is equal to the change in kinetic energy, as well as the fact that the work, in general, equals the force times displacement. We can set these two equal and solve for the average force that the object would undergo. Now, since phones usually don't leave a little penetration hole into the floor when you drop them, the thing that we'd probably do here is measure the depth of a dent on the side of the phone. So if we dropped our phone, picked it up, measured how deep the dent was, we could use this and plug that in and find the average impact force that that phone was probably subject to during that collision. If we take a range of depths for these dents, then we could predict a range for the impact force for the phone. And we see that the smaller the dent, the greater the impact force. However, the interesting thing here is that this is also the average force that the phone experiences. And we are wondering if at some point during the collision, the phone feels a force that is much higher than this, or a true maximum. And this is what I'm going to try to address next. I'm going to use a classic physics approximation and say that the phone is pretty much a spring. In order for that to be useful, you need to find the spring constant. To find the spring constant, you need to do some materials testing. Fortunately, last year with the iPhone 6 bend gate, lots of people were posting videos and results of 3-point bend tests of their phones. And taking the data from one of these tests, I was able to determine the Young's modulus of the iPhone 6 Plus and the spring constant of the iPhone 6 Plus. Now, this spring constant can be used to help us determine the impact force. To use our newly found spring constant to determine the maximum force on the phone during the collision, we'll have to say that the maximum force is going to be when the most energy is stored in the phone, or in the deformation of the phone, because we're treating it like a spring. So when we say that all of the phone's initial potential energy is in the form of spring energy, that's going to be when the maximum force is taking place, or the phone will be maximally deformed or bent due to the forces involved in the collision. So setting these energy equations equal to each other, we can solve for this maximum displacement. And plugging this into Hooke's law, where the force equals the spring constant times the deformation or displacement, we can solve for the maximum impact force of the phone during the collision. And we get an equation that we'll be able to plug in for these variables. So, when we plug it all in, we see that the phone is subject to 1,462 g-forces. Now this sounds like a lot, especially since we know that pilots can only sustain about 9 g-forces while during turns. However, the thing about g-forces, in order to convert it to a regular force in newtons, you also need to know the initial weight of the object under normal gravity. So, when we plug in the weight of the phone, we see that it would feel about 2,000 newtons of force while undergoing these massive amount of g-forces during a drop. However, the fighter pilot, who would weigh 150 pounds, would be undergoing a force of about 6,000 newtons. So, in order to get to the bottom of g-forces, you have to understand that lighter objects take g-forces much better than heavier objects. And I think this is part of the real confusion about g-forces and what they mean. Thank you.